Hello, dear students. Hope you are doing well. Today I'm going to explain the last part of chapter 19, Acids, Bases and Salts. The objectives that I hope you will understand at the end of the lesson are: describe when a solution of a salt is acidic or basic. The second objective is to identify the components of a buffer. So, let us begin with introduction by asking you several interesting questions. The first question: how is the pH of blood controlled in the human body? The answer for this question will be at the end of the lesson. The second question: what is the normal pH of a human blood? It is 7.4. The third question: what is the safe pH range for human blood? It is between 6.8 and 7.8. The last question: can a person survive for more than a few minutes if the pH of the blood drops below 6.8 and rises above 7.8? The answer is no. So, this lesson will explain the process that prevents such a life-threatening event. The first objective is: when is the solution of a salt acidic or basic? Let us recall that a salt is one of the products of a neutralization reaction. So, can you answer these questions? Start with the first one. What types of acids and bases were involved in the neutralization reactions? Let's try to remember. The answer will be strong acid and strong base. The second question: what were the products of these reactions? Do you remember? The products were a salt and a water. The third question: what is the pH of the equivalence point when a strong acid and strong base neutralize each other? It is 7. Now we are going to explain a graph by comparing the titration curves for a weak acid and a strong base with that for a strong acid and a strong base. We have also several questions about these two curves. Here, examine the curves well. The red curve is for the acid-base titration. We call it A, which is weak acid and strong base. The blue curve is for titration of strong acid and strong base, and we call it B. Now the first question: what is the pH of the equivalence point for each titration? Examine the curve well. If we ask you with respect to A, so it is between 8 and 10. The answer is 8.7. With respect to B, it is 7. Do you remember that the equivalence point of strong acid and strong base is 7? Now, the second question. What ions are present in each solution at the equivalence point? With respect to A, they are Na plus, OH minus, CH3COO minus. Now, with respect to B, the ions are Na plus and Cl minus. Now, the third question, what are the equivalence points of the two titrations different? Why are the equivalence points of the two titrations different? The answer, due to the strength of their reactants. What does it mean? In titration A, the CH3CO-, which is the ion present in the solution at the equivalence point, can react with water to produce OH-, while in B, the salt solution is neutral, which means that Na plus and Cl- do not react with water. So what will be the conclusion? The pH at the equivalence point for the weak acid, strong base titration is basic because it gives OH- in the solution, while the pH at the equivalence point for the strong acid, strong base titration is neutral because it gives Na plus and Cl-. These ions do not react with water. So the difference in pH exists because hydrolysis occurs with some salts in solutions. To understand it well, let's take the example that CH3COH, which is ethanoic acid, which is weak acid, reacts with or neutralized with NaOH, which is sodium hydroxide. Remember that sodium hydroxide is a strong base. These two reactants give the salt and water. This salt is CH3COONa. Its name is sodium ethanoate plus H2O, which is water. Now, what about this salt? This salt is completely ionized to give CH3CO- plus Na+. So these are the ions that will be present at equivalence point. Now, what does this CH3COO- behave in water? How does it behave? Let's see here. CH3COO- plus water, it reacts in a reversible reaction to give CH3 COH plus OH minus. Remember that CH3COO minus is Bronsted base because it accepts a proton from water, from H2O, to become CH3COH by gaining this H plus and giving OH minus in water. So OH minus in the solution is the conjugate base of H2O. So this solution is basic, so salt here is basic. We can express the couple of acid base as CH3COH dash CH3COO minus. We always write the couple acid base. So here the salt is basic because the CH3COO minus reacts with water to give OH minus in the solution. We say reacts with water or hydrolysis occurs. How do neutralization reactions that produce a neutral solution at the equivalence point differ from those that produce acidic or basic solution? So here it depends on the strength of the reactants. We can say when a strong base and a strong acid react, the solution is neutral. So the salt that we get is a neutral salt. When a strong base and a weak acid react, the solution is basic. It means the salt is basic. When a strong acid and a weak base react, the solution is acidic. It means the salt is acidic. Let's take an example of the last one. NH4OH, which is called ammonium hydroxide, it is a weak base, react with a strong acid, HCl, hydrochloric acid, to give NH4Cl, which is ammonium chloride, it is the salt, plus H2O is water. Now, what about this salt? Is it acidic? Is it basic or neutral? This salt is completely ionized in water to give, as you see here in the equation, NH4 plus Cl minus. What about this NH4 plus ion? NH4 plus ion reacts with water or hydrolyzed in water to give NH3 plus H3O plus. Now examine this equation, this reversible equation well. NH4 plus is Bronsted acid. Why it is Bronsted acid? Because it donates H plus to water, to H2O. So the NH4 plus becomes NH3 and the water becomes H3O plus. It means here the NH4 plus hydrolyzed in water to give H3O plus, that makes the solution acidic. So hydrolysis of this salt gives H3O plus, the salt is acidic. And the couple of acid base can be written as NH4 plus dash NH3. Conclusion here, we can say strong acid, when it reacts with a strong base, the salt that we get is neutral salt plus water. So remember, strong with strong gives a neutral salt. The second conclusion, strong acid react with weak base. The salt is acidic salt plus water. So the strong acid gives acidic salt. The last conclusion, weak acid will react with a strong acid. The result will be basic salt plus water. So this salt is basic because the base is a strong base. So here, strong acid with a strong base gives a neutral salt, strong acid with weak base, acidic salt, weak acid with a strong base gives basic salt. Now, we want to start with the second objective, which is what are the components of buffer. Let's take two beakers. The first beaker, we put in it 1 liter of water, so we can call it unbuffered solution. In the second beaker, which is buffered solution, we put 1 liter of ethanoic acid with sodium ethanoate. Now, what do we do here? Suppose that you add 10 milliliter of 0.1 molar sodium hydroxide to 1 liter of water. What do we observe? The pH will increase about 4 pH units. It means from 7 to 11. This change shows a relative increase in pH. It means the pH increases relatively high. Now, consider a solution containing 0.2 molar of each ethanoic acid and sodium ethanoate. The pH is 4.76. Add 10 milliliter of 0.1 molar sodium hydroxide to 1 liter of this solution. Now here try to see the difference. The first one, the difference that the first one is 1 liter of water, the second beaker is ethanoic acid with sodium ethanoate. Let's see the similarity here. We add the same amount of sodium hydroxide to both beakers. Now, in the second beaker, the pH will increase 0.01 pH units. It means from 4.76 to 4.77. What do you observe here? This change shows a relatively small increase in pH. Now let's try to compare. In the first beaker, the pH changes relatively high or increasing by 4 units, while in the second one the change will be the change in pH is relatively small, or the increase in pH is relatively small. What will be the conclusion here is that The solution of ethanoic acid and sodium ethanoate is an example of buffer. So, what are the components of buffer? The components of buffer will be the weak acid and its salt. So what is a buffer? A buffer is a solution of a weak acid and one of its salt, or a solution of a weak base and one of its salt, where the pH remains fairly constant when small amounts of acid or base are added. So example of buffer solution, it is CH3COH and its conjugate base, which is, or it is the salt CH3CO minus, or it can be NH4 plus and NH3. So here buffer is a solution that consists of weak acid and one of its salt, or a weak base and one of its salt, and the pH here remains constant when small amounts of acid or base are added. Now, what is the capacity of a buffer? Is the amount of acid or base that can be added to a buffer solution before a significant change in pH occurs. Now, let's go back to the first question I asked in the introduction. How is the pH of blood controlled in the human body? Is answered below. The optimal human blood pH is maintained with the presence of two buffer systems. These systems include dihydrogen phosphate ion and hydrogen phosphate ion. The formulas can be written as H2PO4 minus, this is the acid, and its conjugate base HPO4 2 minus. The buffer pH is 7.20, and the second buffer system in the blood is carbonic acid hydrogen carbonate ion. It is, how do you write the formulas or the couples here? H2CO3, it is the acid, and its base is HCO3 minus. The buffer pH is 6.46. Now, application on buffer solution. Which of the following pairs can form a buffer solution? NH3 and HCO3 minus, or C6H5COH and C6H5COO minus? What do you think will be the answer? It is pair B, because it consists of a weak acid and one of its salt. Finally, I hope that all of you found interest in this chapter. Thank you.